In the last couple of weeks I experimented a lot with deforming cylinder bars into rings, forming a chain and sliding it along a curve. Rendered out several versions and got a pretty good response on my social networks. What started out as a simple project ended up expanding more and more, stacking one transformation after the other. It wasn't as straightforward as I thought in the beginning, but I managed to pull it through and thought you might be interested in learning its inner workings. You might quickly think they're just instances sliding along a curve. I initially thought so too. The key to this effect is bending the bars into rings. Unfortunately, animating each ring separately is not possible if all rings are instances. So you have to be smart and stack one transformation on top of each other. If I got you intrigued, grab yourself a cold drink and follow along. Start with a straight curve line. Resample it to create more divisions. Add a curve to mesh and feed it an arc curve. We will generate two concentric rings using two half-circle profiles. Set the resolution to 8 for now, radius to 0.05. You can always tweak these parameters later. Start angle to 90 and sweep angle to 180 degrees. Check both connect center and fill caps options. Now let's use the same arc as the base for the other semicircle ring. Add a transform node. Rotate the geometry 180 degrees in the z-axis and join the result with the previous version. To better visualize both rings, store a named attribute with a unique value for each half. Call this attribute color. Use a value of 1 and -1 on each arc. Now set a material. The default one is fine. Switch the 3D view to Material Preview mode and hop to the Shader Nodes editor. Connect a Mix Color node into the base input of the principled BSDF shader. Darken the second color input to be able to see a difference. We'll drive the mixing factor by the value of our color attribute we set up earlier. As you can see, the main cylinder bar is ready. Turn back to the Geometry Nodes editor and group together the nodes that make up the cylinder bar. Now comes the key part of the whole tutorial, building the simplest band deformer. Add a reroute and group it. Call the group simply Band. Bending an object can be thought of as rotating its points around a center position on a given axis. Let's start with that. Use a set position. Feed a position field to the position input and insert a vector rotate node. I'm choosing Y as the axis of rotation. Drag the angle handle around and you see that the cylinder rotates as a whole. We surely don't want that, but it's a start. We want the points to deform less at the bottom and more towards the top. The total height of the cylinder represents the length of the circle, which will stay constant during the deformation. We can calculate it by using the bounding box info. Subtract the minimum vector from the maximum and get the z value from the result. Now, the formula for any arc is length equals angle times radius. As I said earlier, during the bending process, the length will remain constant, so the only varying elements will be the angle, controlled by us, and the radius. To get the radius, we divide length by the angle. For a line to bend into a full ring, the rotation applied must be in the range of a full circle. Let's use a mixed node, set the range from 0 to 2 times pi. Now we can control the bending factor using a simple 0 to 1 factor slider. Feed the result into the X component of a combine XYZ node and connect the outcome vector into the center of the vector rotation node. Play with the angle slider. It's still not what we're after. The cylinder still rotates as a whole, albeit from a different center. But we'll get there. We need to rotate each segment a different amount. As the points get higher, they should be rotated more. Let's divide the point's Z coordinate, which increases as it reaches the total arc length, by our radius. The result will be the angle each segment needs to be rotated for the cylinder to form a circle. Feed the result into the angle input. Now, playing with the factor value, you will notice that although each segment rotates a different amount, the shape doesn't resemble a ring at all. More like a spiral, really. What does this mean? As the Z coordinate increases, so does the radius. Why does this happen? At this point, I almost gave up myself. I knew the solution was close, but couldn't grasp it. Then I got it. How do we keep the radius constant? What if we zero out the Z component of the initial position? Let's combine a new position vector, but this time leave the Z component to 0. Now we're talking. A working bend modifier, but there is one tiny problem. If the factor is equal to 0, the cylinder height shrinks to 0. In fact, we're dividing a value by 0, which mathematically doesn't make sense. We'll use a switch node to get different results based on the angle value. If the bend factor is equal to 0, the switch value will be false. We'll feed the original position into the false socket, otherwise the result will be true and it will return our rotated position vectors. And there you have it. You've built yourselves the simplest bend modifier, which you can mark as an asset and reuse on any other project. But this project is about building a chain of rings. So we'll modify this node group a bit. I would like the center of this geometry to match the center of bending. Tab back inside. It's just a matter of offsetting the geometry in the X direction. But by how much? That would be the same amount as the radius of the circle, right? We find the radius of a circle by dividing the length of its circumference by 2 times pi. Combine the result into a new vector and feed it to the offset socket. We need to offset the geometry in the negative X direction, so negate the 2 times pi angle. Tab out of the group and play with the bending factor. Experiment with other parameters also. For my project, I bent my rings from the middle by changing the curve line Z position start to 0.5 and the end to positive 0.5. To make the ring smoother, you can increase the resample count. This was the hardest part of the setup. Now let's continue with the rest of the project. We will duplicate the ring along a spline, in this case, a circle. You might be tempted to instance them directly on the circle points. Try bending. It doesn't work, does it? We need to realize the instances first. Try bending now. The cylinders bend okay, but it doesn't work as expected, as you can see. The problem lies with the order of operations. Currently, we're bending each bar after it's positioned along the spline. Instead, we should bend them in place and only afterwards orient and position them along the circle. How will that work? We'll not instance the chain of rings on the circle points directly. Sever the connection to the point socket. In their place, feed it a mesh line node and set the offset Z value to 0. This way, whatever point count we enter here, the chain links will be generated at the center of the 3D world and they will bend correctly. Remember, we are realizing the instances before bending. But how will we be able then to orient and place these transformed meshes along the spline? Simple. We will sample the circle curve based on the index number of every point and store the position along it as a vector attribute. Enough theory, let's do it. Insert a store named attribute after the mesh lines node. Change the domain type to vector. Call this attribute pPosition. Add a sample curve to the circle. Feed the position output to the named attribute value socket. The vector will be driven by the index number divided by the total number of points. Instead of placing each point physically along the curve, we are storing the position along the curve as a point attribute, which will be inherited by every instance down the node tree. That way we can use that attribute to offset the meshes around in 3D space. Now, append a set position node after bending takes place. Feed a named attribute to the offset socket. From the names drop-down, choose pPosition. You can see the cylinders jump into place. Now, let's test the bending. It miraculously works. I told you it's a question of the order of operations, didn't I? Positioning along the spline should happen last. This project will necessitate a series of transformations like this chained together. So, to better keep track of them, it's a good idea to frame and name them something that makes sense. We'll apply the same idea for orienting each ring along the curve. First, store a new named attribute of type vector called pOrient. We already sampled the curve. Let's make use of the tangent and normal vectors to calculate the orientation. Feed the normal direction to the vector input socket of an Align Euler to Vector node. This is a very interesting one. Blender's manual explanation about this node is a bit vague, so let me try to clear the mystery out of it. We feed it an orientation, or otherwise called rotation vector, and a direction vector. This node is designed to calculate the rotation needed to align one chosen axis of the orientation to the direction vector we feed it. In our case, the cylinder has no rotation applied, so we're not connecting anything to the rotation input. The bending happens around the y-axis, so we choose this one as the axis to align with the normal vector. Now, feed the resulting rotation vector to the rotation input of yet another Align Euler to Vector node. Select the x-axis of the rotation vector for alignment. This time, connect the sampled tangent to the incoming vector socket and send the result into the value input of a named attribute node. What have we done here? In short words, we first calculate the rotation needed to align the y-axis of each ring on the sampled normal direction along the curve. Then, we align the x-axis of this rotated vector to the sampled tangent direction. I know it sounds scary, but this way we are guaranteed that each ring orientation along the curve is rock solid, no matter the curve shape. Let's apply this orientation to the individual rings now. Position along the curve will be the last step, so insert another set position node before it and feed a position field to the position socket. Use a vector rotate. Remember, the pOrient stores an Euler rotation vector, so we need to change the rotation type accordingly. Connect the named attribute node to the rotation input and select pOrient from the names list. Great success so far. Chain links are cross-connected. Next step is to rotate every other link 90 degrees on the x-axis. Again, same concept. Store an attribute to mark each ring as either even or odd, and use that attribute value to rotate every other one 90 degrees on the x-axis. Set the attribute type to Boolean, call it p_even/odd. An index number followed by a modulo operator with a base of 2 will assign values of true or false to all the points that serve as seeds for our chain links. This way, we will have all the even-numbered rings marked for rotation. Insert another set position before the orientation step, and again use a vector rotate after the position node. The axis of rotation is x. Connect the p_even/odd attribute into the angle input. You can see the rings reorient, but only by 1 radian angle. That's because we're feeding either zeros or ones as the angle input. Multiply the attribute by half p. Now we're talking. Frame these nodes and call them rotate even/odd. Increase the point count so the rings interconnect. If you want to directly link the length of the curve to the number of links, you can do so. Add a curve length node after the circle and multiply it by the ratio needed for the rings to nicely fit into each other. From here on, we have a chain that automatically extends to the curve length. Increase or decrease the circle radius to test it. How do we slide the chain along the curve? Easy. We add some value based on the time to the factor input of the sample curve node. First, make sure to have a fraction operation as the last step, then insert an add node after the division. Feed a time in seconds to the remaining free input and divide it by an interval of time, let's say 20 seconds. This makes each chain encompass the whole length of the curve in 20 seconds. And because we use a fraction operation, when reaching the end of the curve, each link will start sliding again from the start, giving the impression of continuously looping around. The position along the curve, that is the factor value, will be essential later on for the animation stage. It will determine the right time to move the cylinder bars into place, bend, slide along the curve, unbend, and move away from the circle. So let's store it as an attribute unto the seed line points. Call this one p_factor. This attribute will be inherited to all the points of the rings, and we will use it to animate bending and transformations. Make some room before the bending node group. Feed a named attribute node to the bend input and choose p_factor as the attribute to drive the deformation. This way, each ring starts bending when it is at the start of the curve and is bent completely as it slides towards the end. In my original video, I bent the rings at the start and straightened them at the end of their travel along the curve. To recreate that effect, insert a map range node and change the input range from 0.1 to 0.15. Every bar now fully bends to a ring only at the tip of the curve. To control the straightening, add another map range. This time, set the input range from 0.85 to 0.9. Combine both results by subtracting the second from the first. Hit play and see the preview. The result is a constant flow of bars bending as they start their travel along the curve and straightening when they reach the end. Now let's offset their position so they move towards the curve in the beginning and leave it in the end. Again, use a set position node. We'll drive the z-axis of the offset vector by the p_factor attribute. Add a combine xyz node and connect the p_factor value into the z-axis. We only want the offset to happen at the start and the end of the curve, right before bending and just after the straightening deformation. So we'll map the p-factor input range from 0 to 0.1. That covers the beginning. Set the output range from 3 to 0. Then add another map range. This time the input will range from 0.9 to 1. And the output range from 0 to 3. Combine both results by adding them and hit play. You can see that both range maps cancel each other out. You may ask how I came up with those numbers. I would love to say that they happen to come out of the top of my head, but I would be lying to you. The truth is I experiment a lot, tweaking the numbers, analyzing the results and making notes. These are the best results I found. Feel free to change them at your heart's content. As an optional step, I added some tilting motion to the chain after the offset. Insert a final set position node, and this time we will rotate the position vector on the x-axis based on the p-factor attribute. Insert a map range and set the input value in the range from 0.3 to 0.7. This covers the range from the end of bending to the start of straightening. During this interval, let's rotate each ring from 0 to a full circle, that is 2 times pi. Hit play and see the result. Now, because I started out with a Bezier curve and put the geometry node as a modifier on it, you can swap the circle with not only any of the primitive splines that come in geometry nodes, but also any custom shape that you can draw directly in the 3D view. The setup should work without major tweaks. I guess you can push this project in any direction you like. In another version, I used the color attribute to offset each semicircle ring in opposite directions. The main takeaway from it is that you get dramatically different results by changing the order of operations in deforming the geometry. In this case, we cloned the bars in the center of the 3D world, bent them in place, oriented them along the length of the curve, and only then placed them in position along it. This video went on longer than usual, but I hope that you enjoyed it and learned a new thing or two. If so, please share the knowledge.